Hello, everybody. Thanks for coming. I'm very excited to talk to you today about tackling the limits of deep learning for natural language processing. But before I do that, I want to do two things. One, wish everyone of you a happy Women's Day. I wouldn't be here without the awesome woman in my life, especially my awesome mom. Now, another announcement is that, why am I talking about the limits of deep learning for NLP and not for computer vision? And part of the reason is that computer vision, to a large degree, is solved for a lot of the use cases that really matter to a lot of people. So we actually just yesterday announced sort of general availability for anybody to create their own custom image classifiers. And basically you can drag and drop or use very simple code and then integrate that into any kind of workflow that you might have in a pretty general purpose system. So Einstein Vision is one of the Salesforce products that were just announced as GA. And on top of that, we also have some really fun applications. So here, oh boy, I can't see it. So beyond just classification, we also have object detection. And so here's a fun use case for object detection where you might want to count what you see in a cooler. Also something we just announced yesterday. And let me see where the test cooler is. We had a live demonstration. We brought a cooler yesterday. But here, I think this crowd will appreciate some detail. Namely, as you zoom in here, we have bounding boxes for all these different items in the cooler. So not just object general sort of classification, but also object detection, identifying specific entities and exactly what kinds of entities they are and being able to count and all that. All of that is now possible in computer vision. And because of that, in terms of tackling the limits of research and going a little more technical, I'll focus on natural language processing. So with that, let me get started and say that I think in general, the field of artificial intelligence has gotten very good at taking a single task, data set, model, and metric, and then optimizing in that kind of setting. And thanks to end-to-end trainable deep learning models, the speed of these improvements on single tasks is increasing more and more. However, if we continue to start all our projects from random parameters, we won't ever obtain a single NLP model that can understand language in all of its complexity. A single unsupervised task is unlikely the solution either, since language has a lot of different kinds of supervision and feedback, requires solving a lot of different kinds of tasks, right? So we need logical reasoning, we need visual reasoning, we need to sometimes retrieve facts from a large database, sometimes we need to retrieve facts from a large corpus of text, and so on. Lots of different kinds of tasks and reasonings are required as we solve general NLP problems and want to have something like a bot that we can have a general conversation with. And so that leads us, or at least led me a while back, to the question of how to express all these different tasks in the same framework. Right? We have sequence tagging, we have sentence-level classification tasks like sentiment analysis, we have a lot of different kinds of sequence-to-sequence models, and so on. And the answer framework for tackling all these different NLP problems that I propose is to essentially think of a joint model for comprehensive question answering. So what do I mean by this? Here are a couple of examples of different kinds of questions and answers that I would like to be able to ask the same exact model. The first example here is something that a lot of people associate with general question answering. You have a couple of simple logical facts, and then you ask a question, and you give an answer. Now, in this particular case here, you couldn't just retrieve the answer through one retrieval process, because when you ask where's the milk, and you find Sandra took the milk there, now you have to do an FR resolution, you find what is there actually referred to, where was Sandra before, you have to find facts about Sandra, she went to the garden before, so the answer is garden. So that's sort of a standard QA task. Now, you could also cast sentiment analysis as a question answering problem. So everybody's happy is the input. The question is what's the sentiment? The answer is positive. You can also think of machine translation as yet another question answering task, where the question is, what's the translation to French? And the answer is the input sentence in French. And you can even cast some of the interesting computer vision problems nowadays as question answering problems as well. Here in particular, visual question answering, where the input is an image, and you ask a question like, for instance, what color are the bananas? And the answer should be green. So basically, in some ways, what I'm arguing for here is to move away from supervised learning as just thinking of an xi, an input, and yi, a classification type of output or a sequence kind of output, and move to, you have a certain input xi, a question about that input, and the answer yi to that question with respect to that input. So now this is the first sort of motivation to lead us towards a bunch of different obstacles, and they're getting quite technical, and I hope that this crowd enjoys diving a little bit deeper into some of the research that we're doing. Now, the first major obstacle towards that goal of having a single joint comprehensive QA kind of model is that we don't even have a single architecture, let alone a same model. So what do I mean by what's the difference here? Architecture is, for instance, a support vector machine or a convolutional neural network. That's a general purpose architecture. But now we don't even have a single architecture for that. Now the next level would be to share the actual same weights. So the same exact trained model would be the same. But let's, for now, focus on having the same kind of architecture. When you look at different state-of-the-art models in NLP for different tasks, you actually notice that they're quite different. So for question answering, for instance, it used to be a strongly supervised memory neural network. For sentiment analysis, it was a tree-structured LSTM. For part of speech tagging, it was a bidirectional LSTM conditional random field, and so on. So lots of different kinds of architectures for different tasks. Now, to tackle this, we introduced last year the dynamic memory network. This is essentially an architecture that tries to take in arbitrary inputs, questions, and produce an answer. Now, let's walk through this model in a little bit without diving into too many details for all the different subcomponents. But the main idea is you'll have some recurrent neural network. By the way, if you have any questions, feel free to raise your hand and we'll just make it a little more interactive. Can you raise your hand if you're familiar with an LSTM or GRU or recurrent neural network? Excellent. All right. Well, at least half of the people are going to have fun time. For the other half who are not familiar with recurrent neural networks, think of it as a very complex function that takes as input a word, one word representation at a time, and then tries to compute some kind of representation for the context that you've seen so far, and at each time step might produce some kind of output like, I think so far the sentence is positive, or something like that. So that is a standard recurrent neural network. There's a lot of complexity in there, but we won't be able to go into all those details. So we'll have essentially here a GRU, a gated recurrent unit recurrent neural network, and at each word, we'll basically compute a time step, a hidden representation at that time step at that word. And we'll do this for an arbitrary story. So here the story is very simple, sentences like Mary got the milk there, John moved to the bedroom, and so on. And now we'll have a specific question, namely, where is the football? Now we'll use the same GRU to compute a question vector for this particular question. It's just going to be the last hidden state of that GRU. And with that question in mind now, we will go over the inputs again and try to see which of the facts that were mentioned in that story should we be paying attention to in order to answer this question. So where's the football? Very simply, we'll try to find facts that mention anything about the football. So in this case here, we might think of this last sentence here, John put down the football. It's the last sentence of the sequence, and it mentions football, so it will have a very high attention. Now I'll briefly describe what this attention mechanism is in the next couple of slides, but essentially think of it as a function that takes as input the current question, what I know so far in each sentence, and then tries to compute a score of how relevant does this sentence seem to be for this particular question. Now, as it does that, we have the last module here, which is the episodic memory module. And we're calling these modules because I also think in deep learning we have to move away from thinking of this as one giant model and try to think of it in terms of modules, that each of which talks to the other modules all through vectors. So in feed-forward, the feed-forward computation of this neural network architecture would just pass along vectors, and then we can train this whole architecture in an end-to-end fashion based on the final answer. So in this case here, again, where's the football? John put down the football, gets a very high attention weight. And when there is a large attention being paid to a specific sentence, then that sentence gets given as input to yet another GRU model. And that one we call here the episodic memory GRU. And that one just agglomerates the facts that are relevant so far. So it does that via multiple passes. So you see here the first pass basically captures the memory M1. Now, the model also realizes that that is not enough information. The question is, where's the football? And all I know is that John put down the football, but I still don't know where the football is. But I now, in this vector M here, have agglomerated the fact that John seems also relevant to answering that question. And now this model will essentially go over the input again, and that's why we call it episodic memory. It can pay attention to specific episodes with a certain question in mind. It will go over the input again and now learn to basically pay attention also to facts that mention John. So John moved to the bedroom and John went to the hallway are now getting input into this second sequence. And again, the facts are getting agglomerated in this vector M and then eventually passed to the answer module, which is yet another recurrent neural network sequence model that produces an answer. Now, the main novelty here in terms of these various sequence models is really just in this episodic memory module, which has, instead of the standard GRU, which has a lot of gates that are specific for every single activation, every single unit of the hidden state, here we actually have a single global gate. And that gate is essentially the attention mechanism. And if that gate is very small, then we can completely copy the entirety of the vector from the past state to the next state. Intuitively, what does that mean? That means that if you see a sentence like Mary traveled to the hallway, and your question is, where's the football? You can entirely ignore that sentence. It will not change the states of your episodic memory module. It's really a very focused, recurrent neural network. And the actual attention mechanism is a very simple neural network where we essentially have a couple of similarity metrics between each sentence, the question, and our memory state so far. So again, the question, where's the football? The sentences might mention football or John. M will eventually realize and store in it that John seems relevant to answering that question. And then we have multiplicative similarities and additive, and then absolute values. And these are all element-wise functions. And then we just plug that through a two-layer neural network, have a softmax, and then we can pay attention to these scores. Now, there's a lot of related work to this, and most similar to this is the memory network from Jason Weston that was developed simultaneously to ours. It's actually an interesting pattern that's happening right now with so much excitement around deep learning. When you have ideas, there are usually other people who have similar kinds of ideas. You have to bring them out really quickly. What's unique about our approach here compared to memory networks is that we have these recurrent neural network sequence models as our basic building block in every single module. And that allows us to capture the position and temporality of language in a much more natural way. And that in turn enables us to tackle a broad range of applications. And so we don't just apply this to the Bobby dataset, which is a very simple synthetic question answering dataset, but also to real language datasets such as the Stanford Sentiment Tree Bank. Now, when we look at different hyperparameters of this architecture, we'll notice that sadly, we still can't really have the exact same model solve all these different or give the most accurate possible answers to all these different kinds of questions, because sentiment, for instance, would like to have 2 passes over the input in order to have the highest accuracy, but some of the Bobby tasks require multiple passes over the inputs. So what happens in a sentiment pass? So let's look at a couple of examples of sentences that were incorrectly classified when you allow the model only a single pass over the input, but then were correctly classified when you allowed it 2 passes over the input. The sentence here is, in its ragged, cheap, and unassuming way, the movie works. So these are the kinds of examples that if you want to push the state-of-the-art in sentiment, you now have to get correct. So ragged and cheap and unassuming, not necessarily all positive words. Now, if you just pass over that sentence once, it essentially predicts incorrectly that this is negative. But if you pass over it twice, you'll notice that eventually in the second pass, it actually focuses more of its attention on unassuming and the movie actually working, and then gets it correctly as a positive sentence. Another fun example, the film starts out as competent but unremarkable and gradually grows into something of considerable power. Here again, competent and all the different sentences, all the different words are receiving a similar amount of attention, but once you go the second pass, it focuses more on the considerable power and realizes as a positive. And maybe the last example here, my response to the film is best described as lukewarm. This is a good example of where standard machine learning models based on discrete counts and single words would usually fail, because best is such a positive word. When you sort of just look at naive Bayes weights, for instance, best is usually up there as having some of the highest predictive power for being in a positive class. But after the second pass, it actually realizes that this is in the context of best described, so as an adverb, not as an adjective, and then realize, okay, lukewarm is actually what matters here, and this is indeed negative. So I mentioned that we can tackle lots of different kinds of problems with this, and so I was very excited to see Tsai-Ming, when he joined our group, he actually just replaced the input module of this architecture with one that could go over images instead of over sentences. And he literally did not touch the code of the episodic memory module, the answer module, and the question module, and was able to actually get the state-of-the-art results on visual question answering. So his input module was essentially a convolutional neural network where at the last layer, you essentially have feature vectors for 14 by 14 many patches. And we plug those into a bidirectional GRU to agglomerate these facts. And now these hidden states of this bidirectional GRU are essentially what we, again, can pay attention to according to a specific question, like what kind of tree is in the background. And this architecture at the time of submission had the state-of-the-art on this data set. And you'll notice me saying that a lot, because whenever you have state-of-the-art on anything, it's usually short-lived. Once the project ends and you move on to something else, other people continue working on this data set, and you'll see that the rate of progress is just staggering these days. So almost all the results, as soon as you have a screenshot and you take it, it's usually deprecated a little bit these days. So we can also look at the attention here of this model as it's going over an image with a certain question in mind. So here we basically show the original image, and then on the right we show this completely unsupervised attention aspect of the model. So we never tell the model, look at this particular area of the image in order to answer this question. We just give it a training time, images, questions, and answers, and then it has to sort of figure out itself what to pay attention to get to the right answers. And these are examples from the development set of the data. So here, some simple things like what is the sculpture made out of metal. This one I like in particular because it shows you that the model can indeed overpower the bias that we might have in language. So if I just ask what color are the bananas, you don't really have to look at an image. You 90% of the time are probably correct in just saying yellow, no matter what the image is. But here it actually pays attention to the bananas and then correctly says this is green. This one is a fun one too. What is the pattern on the cat's fur on its tail? Pays attention to largely the tail and mentions as an answer stripes. Here are some simpler ones, like what is the main color on the bus? The answer is blue. This one here is interesting. How many pink flags are there? Pays attention to these pink flags and answers 2. Now, this will not work in the limit. If you have 50 objects and you want to have the model count 50 different kinds of objects, this particular one would not correctly identify a lot of different ones. One, the final classifier here is essentially a softmax classifier, so it has to have seen a specific type of answer. If it's never seen 39 objects as an answer, it will never predict 39. And it doesn't have a very discrete sense and discrete understanding of the world. It's a very continuous kind of attention mechanism that we visualize here in these brighter areas. And so there's still some work to be done for counting. In fact, when you look here at these results, nobody is very good right now at answering number questions. It's still only in the 30s, which is why for specifically counting, you would actually want to incorporate something like object detection, which I showed you on the Coke demo. All right, and here some last examples. Who's on both photos, for instance. I also don't think the model actually understands that there are two photos and then tries to match the two faces and so on. It just finds the majority kind of object in this image, and that is a little baby girl, and so it says girl. But so you might dismiss some of it as just finding clever correlations, but it does surprisingly well on really unseen images, as long as it has seen things in that domain before. So what is the boy holding? The answer is surfboard, and actually pays attention to his arm here and the surfboard. So it's clear that it's more than just sort of randomly guessing things right most of the time. In fact, I showed this demo to John Marker from the New York Times, and we just put this demo together. And I showed him one example, and he's like, "Oh, I want to ask a question too." And I was a little worried because we just put the demo together. And so he asked, "Is the girl wearing a hat?" And this wasn't optimized for production, so it took a while, and I was like coming up with excuses of, well, I have a hard time seeing the hat. It's a black hat on black background, and so on, but eventually got it right. And here are the next 7 questions that after the interview I put into the system, and it actually had, in the end, a pretty good understanding of this general domain. It was the girl holding tennis racket, playing tennis. Was the girl wearing shorts? It's also kind of interesting because it thinks they're shorts, but when you ask what color is her skirt, it says white, so it has some kind of robustness, and I actually wouldn't know exactly what it is either. Then what color is the ball? That one was a good one because I first asked what color is the ground, that's brown, but then brown is again the majority color, so I chose like the smallest object in the image, and it actually picked up the ball and its color here and correctly classified this as yellow. Now, when I broke it, it was actually the 9th image that I don't show here. So what did the girl just hit? Tennis ball. And then I thought, okay, what if I ask, is the girl about to hit the ball, or has the girl just hit the ball? And it said yes in both cases. So then I was like, all right. Still hasn't seen all the correlations of what do the arm angles look like and so on when you have already hit the ball versus you're about to. All right. So that was our first step towards trying to tackle the first major obstacle towards comprehensive question answering, and that is having a single architecture. Now, the second obstacle is that we actually want to jointly train all these different tasks and models in a single model that actually shares the weights. And when I say fully joined multitask, I actually mean it in an even harder sense than a lot of the academic literature right now, which usually thinks about just having a source task and then a target task, and then shows that after having trained on some model on a source task, you transfer the weights and you do better on your target task. Usually, so this is something that you see in computer vision, for instance, where everybody pre-trains their convolutional neural networks on ImageNet, and then they just copy over those weights and then train something else. But nobody actually looks back and say, did training on the second task actually improve or worsen my performance on ImageNet? And the default answer is, in most cases, it just gets worse. So we also, in many cases, restrict it to the lower layers. Computer vision is actually a lot better than NLP in the sense that more weights can be shared and are more generalizable. In NLP, we usually only share the word vectors across different tasks. We initialize our models with word vectors, like word to vec or glove, and then everything else on top of that is trained on a particular task. But even in computer vision, we usually have different softmaxes at least, and we might update the top layers of the convolutional neural network. In many cases, people only look at tasks that are actually related when they're trying to train the single model, and they show that relatively related tasks will eventually help each other in some ways. But the truth is, and this is something that is hard to publish and say in the literature, but in many cases, it actually hurts performance, especially if the tasks aren't related, and sometimes even surprisingly when they are related. So trying to have a single model that tackles a bunch of different tasks is very hard. And again, I mean here having everything jointly trained, all the way to having the same decoder or classifier in the end. Now, this is our first attempt at tackling this problem. It's a paper that's under submission right now called a joint many-task model. And it's basically a strategy on how to grow a neural network for solving multiple different NLP tasks. And so in the end, this is quite an unwieldy monster of a model. Basically, intuitively, what's going on here is that we have word vectors and actually character vectors too. And then they get fed into a sequence of deeper and deeper LSTM layers. And the output at each LSTM layer is fed in both in terms of their hidden states and their predictions to the next deeper layer. So we start with part-of-speech tagging, then the part-of-speech tags, as well as the hidden state of that LSTM, are getting fed into a chunking LSTM. That gets fed into a dependency tree parsing LSTM, so trying to understand the grammatical structure of a sentence. And then if you have multiple sentences and tasks that require multiple sentences, such as classifying relatedness or entailment, then you basically have two of these that are fed into the same architecture on top. Are there any questions about high level of the idea of this model? Is relatedness co-reference? So it's a different task. Relatedness basically will just say, given two sentences, how similar or related are those on a score from like 1 to 5 or 1 to 10? It's a particularly helpful task for question answering. Imagine you have an FAQ, and now somebody types in a question, and the question isn't exactly what one of your pre-trained or preset FAQ questions is on your website, but it's kind of a similar question. Then you can, with this relatedness encoder, identify whether they're actually similar kinds of questions. And entailment is a very interesting task in NLP, where you basically want to understand whether one sentence is logically entailed by the other sentence. So saying these 500 people bought this product from company X entails, for instance, that 100 people bought the product, that 100 people interacted with this company, that 300 people made a purchase. And I could come up with lots of different kinds of examples of things that are logically entailed by another statement. So it's, in the limit, a really, really hard task in NLP too. Now, I'm just going to show you a couple of insights that this paper has. Actually a very rich paper, like 11 different tables and lots of ablation studies and so on. But the first thing that is important to note is that we actually use character n-grams too. So character n-grams essentially are trained in a similar fashion to word2vec, but you average all the character embeddings for each word, and then you try to predict surrounding words. That way, you never actually have an unknown word anymore in your input. That's very powerful. And then as you move deeper and deeper, you will take, again, not just outputs and the hidden states, but also the outputs of the previous layers. So you have part-of-speech tagging here, and the part-of-speech tagging outputs and the hidden states are getting fed to chunking, and then the chunking and part-of-speech tags and hidden states are getting fed, for instance, to the dependency parsing. And another important idea here is that we call sort of successive regularization, where once you train a model on the first layer, the part-of-speech tagging layer, for instance, you want to not change the weights too much, but you still want the higher level tasks to be able to modify the lower level tasks so that it's actually jointly trained. And the way we achieve this is by the simple regularization term, where we basically say, don't move away too far from the best weights from the part-of-speech tagging model that got you close to state-of-the-art on that, but you can deviate a little bit. And this delta basically here is a parameter that changes how fixed you want to be and how much you're allowed to change the lower level layers as you train on more complex tasks. So this model actually got 4 state-of-the-art results on some very competitive benchmark data sets that many people have been working on for many years, sometimes even more than a decade. chunking, dependency parsing, semantic relatedness, and textual entailment, state-of-the-art numbers. All right, on to the third obstacle, and that is that all the NLP models I just described and pretty much everything you see in the literature can never predict words that it's never seen before. In the end, we always have a softmax classifier to predict some kind of output. So in the simplest case, for instance, let's do language modeling, the task of trying to predict the next word so you can understand which sequence of words is more likely. Say, it's very useful for, say, speech recognition, where you might ask, what's the price of wood? And now the default would be that the would be the W-O-U-L-D, auxiliary verb, would I like to do something? But in this context, the price of wood, it's much more likely the W-O-O-D. And so understanding and being able to predict the next word and giving different probabilities to these is a very useful task in several cases. And the problem is here that we'll always give 0 probability or some very small smooth probability to words we haven't seen in the at training time. And so to tackle this, this paper here at ICLR that we'll present in April there on essentially having a mixture model of a standard softmax, the standard classification paradigm, together with a pointer. And so this is done by Stephen Meredy, who sits right there in the back. Wave everybody. Right, there he is. He was here earlier. And basically, the idea is that at each time step, you have a pointer, and you can have trained a pointer to point to previous words in the input. So let's look at this intuitive example here. Let's say the Fed Chair Janet Yellen, something, raised rates, and then in the next sentence it says Mrs., and now you want to predict the next word. But let's say Yellen was a very rare word and it actually didn't appear in your training corpus. Now, previous models would just never be able to predict Yellen, but this model can learn to actually point to this particular word and then use the pointer instead of the softmax. And then there's also a Sentinel, which is all the remaining probability mass if the model isn't sure to which words to point to, and then it can use the standard softmax. So it's a nice mixture model between these two. In general, we don't have to go into too many details of this architecture. It's also a recurrent neural network type sequence model with this particular addition here of having a query vector and then a softmax over all the previous words, simple sort of inner products between this query vector and the hidden states of 100 words before. And you combine both of these in the end with the softmax and these pointer distributions. Now, we tested this on the language modeling task and the Penn Tree Bank, which is a very commonly used data set. We actually introduced another better data set too, and it improved the state of the art on this data set. Now, what this model also had as a problem is that essentially when you carefully look at all these language models that we have and deep learning models in NLP, you'll observe that they actually all have 2 word vector representations. They have the standard word vectors that you know and love from word2vec or clov, but then they also have the softmax over all the words. And the softmax weights can essentially be seen as another word vector representation that is just for the output embedding. And so this was a great project of 2 students from my class from last year, Hakan and Kashayar, who essentially had this simple but theoretically very well motivated idea to tie the word vectors and the softmax weights for every word and actually force them to be the same in the model. And that again improved further the perplexity, so lower is better here. The model is less perplexed about seeing the next word. It gives higher probability mass to the correct words. And for a model and data set for a data set that's been around for a long time, we actually see an incredible progress here on this task. And these numbers are just going down much more quickly than they had in previous decades. Now, maybe I'll skip this obstacle because it'll take a while, but high-level idea is that when you ask a question about a certain input, sometimes you actually have to reinterpret the question given the context and given the input. So the idea here is, for instance, if I ask you, like, may I cut you? Then that is a very different interpretation as a question if I'm holding a knife or whether you're standing in line, right? And so you want to make sure you understand exactly what the question means given the context and the input. And so we introduced this co-attention model and got state-of-the-art at the time of submission on the Stanford question answering dataset. Super interesting dataset for question answering. It has 100,000 different question answer inputs over Wikipedia and a nice leaderboard. It's very well organized. Now, the last obstacle that I think is very important to tackle here is that recurrent neural networks are incredibly slow. And you've noticed that we now use recurrent neural networks as the basic building block in all these different models that I described. And so what we'd like to do is speed them up, especially using multi-processing types, multiple processors, GPUs. And this is another paper that we'll present at ICLR on quasi-recurrent neural networks by James Bradbury and also Stephen and Siming. And basically, the idea of this model is to combine the best of both worlds, namely the sequence nature of LSTMs that gives us a hidden state, a hidden vector representation we can use for classification at every time step, but also those of convolutional neural networks, which are great because they can be parallelized very well across multiple cores and GPUs. And so when you marry the best of these, the child becomes a quasi-recurrent neural network that is essentially a first layer that is parallelizable across different time steps, and we can cast that as a convolution. And then the pooling layer is parallelizable across the different feature channels. So you have different types of parallelism that are basically going back and forth, and in the end have a very, very fast model. In fact, when you train this, we can look at sort of where most of the time is spent now, and for the quasi-recurrent neural network, the majority of it is actually just in the softmax, trying to predict the words as the output and just general optimization overhead as you train. And you can get somewhere between 1.4 to 16.9% or x speed up, so x, not percent, depending on how long your sequences are and what your batch size is for training. And in some cases, it also works better on language modeling or on sentiment analysis. And it also gives us some very nice and easy to interpret features that you can look at. We have a nice blog post if you search for the quasi-recurrent neural network paper online. There's an interactive blog post where you can see each neuron as it changes over time. Here, just have a simple example, so not exactly a bad story is around here, and then you can see several of the activations turning to basically capture that's a little bit more negative, but then at 158, which is right around here, you say this particular review says, I recommend this movie to everyone, even if you've never played the game, and then several of the units become positive again. All right, with that, I want to conclude. Basically, I hope I could show you that comprehensive question answering is an interesting next frontier and way to formalize various different kinds of problems in natural language processing, and hopefully gave you a couple of ideas on how we can tackle this problem. Thanks.
Thank you.